Yeah.
couldn't even, like, after writing few equations on it, you had to just stop using the board.
Goodness.
And then the next day they would be completely clean.
And I have to clean that board outside, the rack that you put up. Because I left some chalk out there and now it's just painted over it in like a one application.
So we are now to chapter 7.
Are you going to open notes there too?
Yeah, loosely. Yeah, I guess technically this is lecture 23. Old lecture 23. So in this chapter, we sort of eventually we leave the narrow confines of surfaces just in 3 dimensions. All right, and so the idea here is to talk about a surface in a more abstract way. All right, and so here's the definition. So M is abstract surface if there exist patches, let's say phi I, di to ui, which is a subset of M, such that phi I and phi j for I not equal to j are smoothly related. And so what that means in particular is, here's my M, right? And so over here I might have, D1, well, let's say DI, and I got phi I. And over here I have dj, and this is phi j, right? And, this one, there's your U2, whereas, that was supposed to be UJ, and the other one is UI. They intersect, all right? So if they intersect, that's where the smoothly related comes into play. Because if they intersect, then you can study the corresponding transition function that you build from them, right? You can look at this function down here, which would be what? To go from here to here, what would that be? That would be, well, it would be, no. It would be do phi I do phi I first, and then I compose it with the inverse of phi j. Yeah, it's fine, it just maps, yeah. So to say that these charts are smoothly related is to say that the corresponding transition functions, these functions down here from R2 to R2, are smooth in the ordinary sense of advanced calculus. All right. And what else? One more. So that means, in particular, this has to be a smooth mapping of R2. So what that means, of course, is that you can calculate partial derivatives of arbitrary order, and they're continuous. Okay. Then we say M is a geometric surface. All right, geometric surface if M is paired with a metric. And the metric, GP, TPM cross TPM goes to the reals. Such that P maps to GP is smooth. All right. And we'll use the notation GP of VW equals angle, Langle V, W wrangle. So use the usual inner product notation. Is an inner product. On TPM. What does it mean to be an inner product on TPM? That means that this metric behaves essentially like the dot product. All right? So what are the, well, by dot product, how does dot product behave?
So you have if they're both going the same way, it should go to 0.
Oh, yes, yes, yes. But I mean, like, algebraic properties of it.
Dot products?
Yeah, like VW, how does VW relate to WV? Right, like the dot product is commutative.
Oh, those, yeah, they're commutative. And doesn't matter which way you put them. They're linear.
Right, they're, yeah, linear.
They're composable.
And likewise for the second slot, right? Like, we can also break up sums in the second slot. And then 3, lose much probably place here. The inner product of a vector with itself is non-negative, and the inner product of a vector with itself is equal to 0 if and only if what? It's the 0 vector, right? So a surface paired with a metric is called a geometric surface. All right. And I say these requirements give us what's called a Romanian geometry. If you replace 1 and 3, you can replace 1 and 3 in different ways to get other kinds of geometry. For example, in symplectic geometry, sometimes you look at inner product, which is, it's not symmetric, it's antisymmetric. In the Lorentzian geometries, you don't have this condition 3. You replace condition 3 with a non-degeneracy condition, which is that the metric has to be invertible in the sense that if you look at its matrix, it's invertible. However, for a Lorentzian metric, you have all of the vectors which if you think about physics, if you think about vectors that correspond to being on the light cone, all of those vectors they could be non-zero, and yet they have 0 inner product of themselves. So like the existence of null vectors makes Lorentzian geometry different than Romanian. Romanian geometry is our happy place. It's where things are most known. It's where mathematicians spend most of their time, classically speaking, because there we have this condition 3, which is, I think, the positive definite condition that the vectors go. Well, I'm not carefully defined positive definite, but this condition here says the only way you can get 0 is vector inner product with itself being 0 is if we have the 0 vector. So that's very useful and simplifying comparatively speaking. Now, I haven't even really, except in my picture here, made clear where the d sub i's are. But I do mean to assume that d sub I is a subset of R2, right? Now, did I say where M is? I did not. It could be lots of things, all right? And however, if you take R2 and replace it with like K, right? If you replace R2 with K, that would describe a K-dimensional manifold. And if a k-dimensional manifold also has a metric at each point, then it's called a Romanian manifold. And so that's that. Okay, so if we have a metric, so given metric can define, what can you define? You can define the length of a vector is the square root of, GVV, and you can define the cosine of an angle to be, this. All right. And so, I can either write this or I can write VV, and this is for each TPM, So here I'm assuming that V and W are tangent vectors in a particular tangent space to the surface. And for those two particular tangent vectors, we can define the length of the vector, and we can calculate the angle between them using the metric like this. All right. Now, all right. So methods to construct metrics, right? How can we construct a metric on a given space? All right. So let's talk about novel metrics. Number one, we can distort an old metric. Old case. In particular, we can let VW equal to V dot W over, say, H squared of P. This is on R2. So we could take the plane and here, this is, H. I say H is H greater than 0 defines geometric surface M. With, we call it ruler function H. Right. And he claims that locally every geometric surface can be so expressed. So locally. Now globally you'll get into trouble because the plane is not compact. So if your surface is compact and you try to say it's the whole plane, it's kind of troubling. The other technique is the pullback. All right, so I told you guys at some point we'd talk about the pullback. And technically speaking, pullback here is a bit of a, this doesn't actually fit in with the larger discussion of pullback, but let me have that larger discussion with you right now because now's as good a time as any. So if I have a surface M, and I have a surface over here, N, and I have a mapping, F, going from M to M. I can connect the tangent space at one point. If this is point P, right, and this point over here is, let's say, F of P, then if I have a tangent vector V, right, I can talk about the push forward this vector over here to the other tangent vector over here, which is so-called F star V, right? So push forward F lower star, it's a mapping from the tangent space at P to M to the tangent space at F of P to N. And there are various ways to define that, but I think the quickest way to express it is just to suppose that F is like equal to alpha prime of 0 for some curve. Think of it as the tangent to a curve. And then the formula for the push forward, F star of alpha prime, is literally F composed with alpha prime. So like the, and also, so like just to draw a picture, slowly but surely I lose my markers. You know, this would be alpha on this surface, right? And then, you know, this is the image alpha. This is the image of F composed with alpha, right? Because F composed with alpha takes this curve and maps it over to the image curve over here. And so you can, you know, calculate the tangent vector to that. That's the push forward. Okay? And I mean, when push comes to shove, if you pick a system of coordinates, all the push forward really is you take the velocity of the original curve and you multiply it by the Jacobian matrix of the map, and that gives you the coordinates of the push forward one. It's really just that. So in terms of my earlier notation, you could also say that this is really just df of alpha prime. You know, that wouldn't be wrong. Okay, so anyway. Now I'm getting off track. Let me erase that. Pullback. What is pullback? Pullback so first of all, if I have, so we can talk about the zero form. So pullback goes from N to M. It takes an object on N and it brings it back to an object on M. So zero form. Maybe you have you know, G, which is a function from N to the reals. All right, that would be a zero form. A zero form on N is a function on N. So the pullback of G, we use upper star in O'Neill for pullback, and that's a pretty common notation. Pullback of G is literally G composed with F. See, G composed with F is a function, which, how does that work? F goes from where? M to N. G goes from where? N to R. So this composite is an M to N to R mapping. In other words, G composed with F is a curve. Well, not a curve. Let's say it is not a curve. Rather, G is a function on M, which we call a function on M is called a zero form. So that's how the pullback works on functions, zero forms. One form, if we have, let's say, alpha. Oh, I've already used alpha as a curve. I'll use some other letter. What should I use for one form? How about, I don't know, what do you want, gamma? So gamma, so suppose gamma is an element of the one forms on N. We could use lambda upper 1n for one form on N. All right, then the pullback under F of gamma is in fact a one form on M. In particular, here's how it works. The pullback of gamma. So how do you define, what does a one form do? A one form acts on vectors to give you back numbers if you're at a point. Or a one-form field acts on a vector field to give you back a function if you want to think about more than one point at a time. A smooth function. Scalar function. So in order to understand what this one form is on M, we need to like feed it a tangent vector. So we feed it V. All right, where in here V is, well, I'll write it in a second, but V is a tangent vector at M. All right, and then that's going to be equal to gamma of something. And I'm doing it at the point P for the sake of specificity here. So how do I get a gamma does what? Gamma is a one form on N, right? So it has to have input into it tangent vectors to N. How do I get a tangent vector to N from this V and this F map? Yeah, how do I get a tangent vector to N? N as in nanu nanu. I've got a tangent, V is from M, tangent vector to M.
Well, then you just use F.
Use the push forward though, right? Use F lower star. Indeed, that is the definition of pullback. The pullback, what it does, the way it works is you take a form, a differential form in the codomain, and then you pick a vector in the domain, and you just push it forward over there and let it act there, and that's how you define the differential form in the domain. That's the pullback. It seems like nothing, but it's actually something. That's the pullback of a one form. How do you do it for a two form?
That's kind of counterintuitive, though. You just assume the pullback just means the inverse mapping path.
But F doesn't have to be invertible. Two form. Let's suppose beta is a two form on N. Then the pullback of a two form on N will be a two form on M. And the way it's defined, well, how do you define a two form? You have to let it act not on one vector, but on a pair of vectors. Right? Two form is defined by acting on pairs of vectors. And the formula is just beta of F star V, F lower star W. And that's for all V and W in TPM. So this is the talk I've been putting off with you guys since we first ran into pullback. Because when I first talked about pullback, this would have been very premature. Like, I hope this makes more sense now that we've been kind of like dabbling in differential forms for a while. But if not, it's I just finished writing the solution to like mission 7, or I think it was 7. There's a question about pullbacks, like problem 89. I actually wrote the solution to that out, and when I repost the solution yet again, the complete solution, hopefully later today, I have them scanned already. The last problem in there actually explores properties of the push forward and pullback and how they're related. But one of the key properties of this pullback is that it plays really nice with the differential and the wedge product. Like, key properties of the pullback are that, like, the pullback of the wedge product of two things is the wedge products of the pullbacks. And the pullback of the differential of a form is the differential of the pullback of the form. So it couldn't be any nicer. I mean, pullback and differential acts so naturally. And the reason for this really, guys, is that what the pullback really is it is a formalization of the concept of substitution. That's really what the pullback is. That's really what the push forward is as well. So the push forward you can think of intuitively as that thing we do in Calculus 3 where we change like partial x to like partial r and partial theta by the chain rule, or we change partial y to corresponding partial derivatives in r and theta, or vice versa. You take the partial derivative with respect to r and re-express it as partial derivatives with respect to r and x. Those are really the push forward of the partial coordinate derivations with respect to the coordinate change map. And this pullback formalism, when you actually see past these like abstract definitions to what it really is, what it's saying is if you have one space and you have like different coordinates on that space, then if you calculate a differential form with respect to one system of coordinates, you can calculate with respect to another system of coordinates by just replacing everywhere the expressions which define the form by the corresponding expressions in the other coordinate system. That's what this identity is saying. It's saying that it doesn't matter if you do the exterior derivative before you make the substitution or after you make the substitution. After you make the substitution. Before. Whichever.
So like when you go from like sphere notation and you change it to back to the reals, it wouldn't matter when you took derivatives of the functions. The derivatives of the functions in like terms of theta, p, rho,
Yeah.
be the same as the derivatives of the function of x, y, z.
Yeah. That in a nutshell is like, that's my intuition. Now it's more general than that because you can define pullbacks and push forwards from maps that are maps of spaces which are not equidimensional. So it has, and those are important for many reasons. But anyway, this is pullback. Now this is pullback of form. Technically speaking, he calls this a pullback metric. It's not a pullback in that sense because this is pullback in sense of form. But here he talks about pullback in sense of metric, pullback metric, which I would just point out, technically speaking, is not part of that discussion because a metric is not a differential form. Because a metric is what? Axiom 1, commutative, right? Differential forms, if they've got two inputs, they're anti-commutative, you know? Differential two form is more akin to a cross product than it is to a dot product, you know? So pullback metric, though, here it is. If you have M as an abstract surface and N as a geometric surface with metric G, so given abstract surface, M, and geometric surface, N, and I'll write N comma G. So this is a nice notation. We could have said that the geometric surface really was M comma G, meaning that it's the set paired with the metric. You know, that's what makes it a geometric surface. It's not just the set, it's the set paired with the metric that makes it a geometric surface. So N is a geometric surface here. And furthermore, you have a regular map. All right. Then allegedly, we can define a metric on M. Now, when I say M is an abstract surface, one of the things I mean by that is even if we have a notion of like distance or something there, we're divorcing ourselves of that idea. We're just thinking of it as a point set. And but here it is, VW M. We're going to define to be what? Well, we want to define it in terms of the metric on N, right? So what we'll do is G of F of P, and then I need to feed it a pair of vectors on N, right? But how do you get a pair of vectors on N if you have a pair of vectors on M? You use the push forward under the regular map, right? The push forward takes you from M, tangent vectors at M, to tangent vectors at N. So I just do push forward F star V, F star W, like that. which I have written, in terms of DF, V, and DFW also there. Now my question to you is that clear that that definition gives us the three properties? Is it giving us commuting, bilinear, and, non-degenerate? I mean, well, what should I call it? Let's call this positive definite. I mean, this is linear in each slot. Well, first of all, it's commuting because the metric on n is given to be commuting, right? So if I flip v and w, I can flip it over here just the same, right? Right? Using the commuting property of the given metric, we get commuting for the new metric. And the linearity that we need in both slots, it follows from two things. Number one, the bilinearity of the given metric, but number two, the linearity of the push-forward map, right? Because the push-forward is linear. So we can pull, we can break a sum. Here, I'll do it in the other slot. So if I've got, V, C1, W1 plus C2, W2, M, that's GFP, F star V, comma, F star C1, W1 plus C2, W2. But then I use linearity of the push forward to pull out the C1 and break up across the sum. And then I use linearity of the given metric on n to break up this sum over here. And of course, that is C1 VW1 plus C2 VW2, which is linearity in the second slot of the M metric, And the other axioms for the metric can be proved similarly, right? They also descend from the Now, wait, one thing though, how about 3? How do I know that only 0 is 0? Maybe I should talk about that a bit. I'll do it up here.
If you're multiplying them and they're the same number, the only way you can get 0 is 0. Or the same vector, the only way you can get a 0 vector is 0.
Can I erase this?
Wait 1 sec.
Okay.
Well, yeah, this proof isn't bad. Yeah, you can go.
Oh, you know what? I'll do it. I'll do it up. I'll do it up here.
Yeah, because if your vectors is greater than or equal to 0, you'd have to have 0 when you dot product it.
But this is not a dot product. This is a metric G this is a geometric surface N. I don't know where that is. I just know that G is a metric. It has these properties. I only have these properties to work with.
Well, then tell me what 3 states specifically.
So the question is, why is it that G? Why can I say that if I have V, VM, right? Why does this satisfy 3? So that's equal to G F of P, F star V, F star V, right? So what do we know? N is a geometric surface. That means G is a metric.
Yep.
So this is given to be greater than or equal to 0.
Yeah.
Wonderful. That's half of the battle. But we also need to know that GM that VV of M is only 0 if it's 0, right? So what happens if this is equal to 0? Well, that implies that this is equal to 0, which means that F star V must be equal to 0. But why does that mean that V is equal to 0?
Well, if F star V is equal to 0,
Mm-hmm.
well, that means the mapping means that if you took 0 and pushed it forward, you would also get, yeah, because if you take nothing from M, you push forward.
But how do I know that? How do I know that that's the only thing that maps to 0? I mean, I agree with you that F star of 0 is 0 for any map F, but this is a regular map. What does regular map mean? That means, yes, but it means that the differential, it means that the push forward is 1-to-1. It actually means that the push forward is invertible. Or
Can you keep invertibility equal to 0?
well, if F star is invertible, that means the only thing that goes to 0 is 0. So like, F star inverse, this exists. So that's V is equal to 0. So hooray, it's because it's the regularity condition that gives us that. So that's all I'm trying to get at here. Okay, so but there's more here. There's something rather beautiful here. Which is, we have to think back to last week. How did we define, what did it take for F to be a local isometry? What was the condition?
Sorry, say that.
What was our definition? F, a mapping of surfaces is a local isometry of what?
Surfaces. Local isometry of surfaces.
Yeah, what did it take?
To get that.
Yeah, I mean, what was the definition of local isometry of surfaces? It was that the dot product, or the inner product of tangent vectors, was preserved if we track so F from M to N, local isometry. If the inner product of V and W was equal to the inner product of the push forward under F of V with the push forward under F of W. And at that point, the only inner product we were working with was what? Just the Euclidean product on all of our three, just the dot product, right? That's just notation for the dot product, really. But this is the natural generalization of that. So now, I mean, we have to expand this definition a little bit, but the definition now is if we have two geometric surfaces, right? They're locally isometric if what? So this was previous. I mean, this is chapter 6, right? Or 5 maybe, I can't remember. 6, 5, I can't remember. 6, okay, 6. So these are both, Euclidean. this notation is just shorthand for x dot y, which is x1, y1 plus x2, y2 plus x3, y3. Right? This is straight up dot product of vectors. We're moving past that now, all right? So what we mean by local isometry at this point should be the following. If F is a mapping from M to N where, you know, M comma GM and M comma GN are, you know, geometric surfaces, then F is local isometry. Means that the inner product with respect to, for the M surface of V and W is equal to the inner product of the N surface of F star V, F star W. So in other words, it's a local isometry if it maintains the inner product of vectors with respect to the concept of inner product of vectors for each of the surfaces. But if you look at our definition of pullback metric, what does it do?
It keeps the three conditions.
Right. Well, yes, but how about that? I mean, what can you say about this abstract surface M and this geometric surface N?
That they're regular.
No. I mean, the abstract surface M, once we give it this metric, which we just proved is a metric, right? Well, then it is locally isometric to N because because the dot product is preserved. I mean, essentially by definition, you force it to be a local isometry. Very sneaky. And then there's a third way. The third way, and third way is often a convenient way. I think there's actually a fourth way, but we'll start with these three. Three is, you know, given E, F, and G on, you know, abstract surface M, you can construct, you know, this such that, like, you say, well, I'm going to say XU is E. I'm going to say that XV is F. I'm going to say that XV is G, and then extend bilinearly. Now, you might not see what's going on here. It might seem like there's nothing being said here because we defined E, F, and G like this before, right? But keep in mind, I'm not saying that the Euclidean dot product is E, F, and G. I'm saying that this is an abstract dot product that's being defined by these conditions. It will not be the Euclidean product, Euclidean dot product for many examples. We'll see an example. All right? Now, so if you don't get three yet, just wait till we get to the example. It'll make much more sense when we get to the example. By the way, just take a second to notice that none of this assumes that M is a subset of R3. All right? So definition, what's a frame field on M? And I sometimes use the notation like this. So do you guys get what this notation means? I'm saying this abstract surface M paired with the inner product Langle-Wrangle. All right. Frame field on this consists of what? Two orthonormal fields typically denoted E1 and E2 on some open subset of M. And in particular, when I say orthonormal vector fields, that means in this context that EI, EJ is Kronecker delta IJ. All right. So like E1 with E1 is 1. E1 inner product E2 is 0. E2 inner product E2 is 1. And likewise, coframe field is like theta 1, theta 2, right? Such that theta I of EJ is Kronecker delta IJ. So you define the coframe field to be the duals to the frame field, just like we did before. Right? In particular, and more than this, I mean, this extended linearly, really. And I say extend linearly because if you define the coframe on the basis, then that suffices to find the linear transformation elsewhere. In particular, just to be more pedantic here for just a second, just like before, theta 1 at the point P and theta 2 at the point P, these are going to be linear maps from the tangent space at P to M to the reals, so-called covectors at the point P. And that's going to be possible for each P in the open set on which we're talking about, all right? So once you have that, then we can define the connection form, omega 1, 2. And we're trying to do this in such a way that we in no way, I mean, we just can't make use of three-dimensional geometry because we don't have it to work with in this context, right? So sorry, I'll get out of your way here in a second. I'm just trying to make use of the whole board, and my camera's a little bit up. Okay, so definition. For this frame and coframe, define connection form omega 1, 2 implicitly via d theta 1 is omega 1, 2 wedge theta 2, and d theta 2 is omega 2, 1 wedge theta 1. Now, remember we talked about this before because I'll write it here. Omega 1, 2 is like omega 1, 2 of E1 theta 1 plus omega 1, 2 E2 theta 2, right? So like just to be explicit here about what I mean by, to be explicit about me being implicit, sorry, it's horrible. You could replace this with omega 1, 2 of E1, theta 1, wedge theta 2. And I'm sorry, I'm writing the 1 and 2 downstairs. I mean to put those up, but O'Neill sometimes puts them. I do like them to be up. I'm going to put them up. And why is that? It's because the one component is the only one that doesn't wedge to 0 there, right? And on the other hand, this one is omega 1, 2, E2. Theta 1, wedge theta 2. Now, how did I do that? I changed omega 2, 1 to omega 1, 2, right? Why don't I have a minus then? So I'm using. So when we take the wedge product of omega 2, 1 with theta 1, the only piece that matters is the part which doesn't wedge to 0, right? Which is the theta 2 piece. So I get omega 1, 2. I mean, my first step should be to erase this and put what? Minus 1, 2, right? Like that. But then minus omega 1, 2 gives me this omega 1, 2, E2, theta 2 piece, right? But then I have theta 2, wedge theta 1. But you notice the expression over here has got theta 1, wedge theta 2. So that's why the minus and minus gave me a plus. So for an abstract geometric surface, if you can calculate the coframe and you can calculate the differentials of the coframe, right? You can compare the theta 1, wedge theta 2, and in so doing, you can calculate the components of the one form omega 1, 2 of E1 and omega 1, 2 of E2, and then use those to construct the connection form. This defines omega 1, 2 without ambiguity. All right? What else do we want to define? I may be getting ahead of myself. I think we might want to, before we define anything, we might want to I think there's a property I got to find here. If I was smarter, I would have written those 3 bullet points on over here and saved them for later. But I'm not that smart. All right, so where was I? I say, okay, so we need to investigate the coordinate dependence of theta 1, theta 2, omega 1, 2. Like, what if we had a different frame? You know? Because if you think about it, as we've dealt with surfaces and we've picked a frame on a surface, it's been somewhat ad hoc, hasn't it? If you think back to explicit examples we did, I was just like, oh, look, well, that's a vector field, and we'll take the cross product with the unit normal, and that gives us a frame, you know? So it's important to ask the question, what if you had a different frame? You know? So what if used E bar 1, E bar 2 with coframe theta 1, theta bar 2, right? So suppose we had a different orthonormal frame on the surface. How do those have to relate? Well, I draw a picture, right? So if this is the E1 and E2 direction, right? Then E bar 1 has to be perpendicular to, well, E bar 2 could either be here or it could be here, right? I mean, there's 2 choices for an orthonormal field, right? Once you pick one, you got plus or minus direction for the other. But I point out that you can define an angle here, right? phi, and you can relate the two frames according to the angle. In particular, E bar 1 is cosine phi E1 plus sine phi E2, and E bar 2 is minus sine phi E1 plus cosine phi E2. All right? And I also write the other one in blue in my notes, right? The E bar prime, that's the other choice. I mean, basically, you could do plus or minus this one, right? So what I say here is I say E bar 1, E bar 2 with the plus have the same orientation as E1 and E2, whereas E bar 1 and minus E bar 2 in my current have opposite orientation compared to the original frame. So, check out my batteries. Uh-oh, well, it's a little sketchy. Still working? Yeah, it's still working. I better take a break and swap that out here pretty soon, though. So lemma 1.4, it says that if you have, given the notation above, if E1, E2, well, let me just say it this way. If plus, then omega bar 1, 2 equals omega 1, 2 plus the differential of the angle. And theta bar 1 wedge theta bar 2 equals theta 1 wedge theta 2. In fact, maybe a better way to write this lemma would actually be just to like we can actually characterize orientability in terms of the wedge product. Might as well do that. I think that's a more useful way to say this. So I'm going to say it this way. If theta 1 wedge theta 2 is equal to theta bar 1 wedge theta bar 2, then omega bar 1, 2 is omega 1, 2 plus d phi. All right? And on the other hand, if the opposite happens, if theta 1 wedge theta 2 is minus theta bar 1 wedge theta bar 2, in other words, this would say that the second frame field is opposite orientation of the original one, then omega bar 1, 2 is equal to omega 1, 2. Actually, was it minus omega 1, 2? Oh yeah, it's just minus this. Minus omega 1, 2 minus d phi.
Now, do you have to, so that's interesting. There's a proof for that when you think that the orientation is just reversed, you just negate everything intuitively.
Well, yeah, the orientation being reversed has to do with like the two form that defines the the two form, which is sort of I want to say it's dual to the unit normal, but I can't say that anymore. Like the orientation is the two form on the surface, and if the surface, is orientable, it has a non-vanishing two form over the whole surface, and so if you think about that, that means you could take that one, multiply by minus 1, sort of flip it over, and that would give you the surface with the opposite orientation.
Yeah.
So.
Yes, intuitive, but still have to prove it.
Yeah. Now, I've got a lot of calculations for this. See if I can find a path through here without doing all